Hello everyone. Now I would like to discuss about design of satellite downlinks. Satellite downlink represents the signal receiving from satellite to the Earth station. The signal which we are receiving from satellite to the Earth station that represents the satellite downlink. So the design of satellite downlink focuses on delivering the sufficient signal quality, that is signal quality will always represented with in terms of CNR, that is carrier to noise ratio. Okay, so the design of satellite downlink focuses on delivering sufficient signal quality CNR to the receiving earth station while minimizing the system cost. Here the minimum required CNR is 14 dB. Minimum required CNR is 14 dB. So here we are calculating the carrier to noise ratio for a satellite downlink system. Okay. So carrier to noise ratio in the name itself, carrier to noise. That means carrier power, carrier power to the noise power. Carrier power is nothing but receiving power of the signal. So here the received carrier power is calculated using this formula, that is PR is equal to EIRP. Here EIRP is nothing but EIRP is effective isotropic radiated power. Effective isotropic radiated power. Sorry. Effective isotropic radiated power. So here the effective isotropic radiated power, which is nothing but the power which is radiating from the transmitting antenna. Power which is radiating from the transmitting antenna. And here GR is the gain of the receiving antenna. Here we have to remember carefully that in downlink, in downlink, in downlinks, transmitting antenna is the antenna which is located at the satellite. Receiving antenna is the antenna which is located on the ground station. So this point we have to remember carefully. In downlink, transmitting power is nothing but the power which is transmitted from the transmitting antenna which is located at the satellite. Receiving antenna represents the antenna which is located on the earth station. So here EIRP, effective isotropic radiated power, the power which is radiated from the satellite, that is PT and GT. GT is the gain of the antenna which is located at the satellite. So PT plus GT. This is the effective isotropic radiated power. And here GR is the gain of the receiving antenna. Receiving antenna is located in the earth station. And here LP is the free space path loss. And LA is nothing but atmospheric loss, and L miscellaneous, that is other losses. So by knowing all these parameters, here we will calculate the trans PR, receiving power PR. By knowing all this, we will calculate the receiving power. And one more parameter we have to calculate is the noise power. We have to calculate is the noise power. Noise power. So to calculate the noise power, this is the formula, that is N is equal to K. K is the Boltzmann constant. Ts is the system noise temperature, and Bn is the noise bandwidth. Okay, so the Ts system noise temperature, K Boltzmann constant, it is given by this, that is minus 228.6 dB watts per kg per hertz. So here terms, all these terms are in decibels. All these terms are in decibels. Okay, that's why the ratio C by N, we are calculating C by N. This ratio, this normal value ratio here in decibels we are getting PR minus N. PR minus N, received power minus noise power. So here we had considered an example, that is C-band downlink, which is operating at 4 gigahertz. C-band we know the satellite communication band, C-band, which is operating at 4 gigahertz, which is operating at 4 gigahertz. So it is operating at 4 gigahertz. So here consider a geosatellite with 24 transponders. The saturated output power, the saturated output power of the transponder is 80 watts, which is equal to 19 dB watts. So here the saturated output power of the transponder, it is located in the satellite. Transponder is located in the satellite. So the output power of the transponder is 80 watts, and converting it into dB, we are getting 19 dB watts. We will assume an output back off of 2 dB, so that the power transmitted by the transponder is 17 dB watts. The global beam antenna, here we are considering the global beam antenna. Coverage of global beam antenna is 20 dB. Here we can see this is the satellite, and the power which is transmitting from the satellite, it is the global beam. So that the gain of this particular antenna, which is located on the satellite, is 20 dB. So here we got the power transmitted by the antenna, PT, and the global gain of the antenna, 20 dB. So that EIRP, effective isotropic radiated power, is 37 dB watts. Now the free space path loss at 4 gigahertz over 4,000 kilometers. Here 4,000 kilometers is the distance from the satellite to the earth station, that is R. So here it is 4,000 kilometers. This is nothing but R. R is equal to 4,000 kilometers. And the operating frequency here is 4 gigahertz. Operating frequency is 4 gigahertz. So the path loss, we have the equation for path loss, that is lambda by 4 pi r lambda by 4 pi r square. Sorry. Lambda by 4 pi r square. So this is the expression for free space path loss. So here by using this lambda we will get from the operating frequency 4 gigahertz, and here r is the distance we already have here. So by calculating this, we will get the free space path loss, that is 196.5 dB, and edge of beam loss is 3 dB. Edge of beam loss also here we have to consider, and atmospheric loss is considering we are about 0.2 dB. Another miscellaneous loss is 0.5 dB. And the at the station gain, here the receiving antenna gain, the gain of the receiving antenna is GR, that is 49.7 dB we are considering. And system noise temperature. System noise temperature, here we are considering 58 Kelvin and bandwidth. And the system bandwidth is 30 megahertz. 30 megahertz. So all these parameters are here. These are the predefined parameters for C-band satellite downlink. C-band satellite downlink. And here the received signal power. We are calculating the received signal power. EIRP is equal to GR, that is gain of the receiving antenna, and the path loss and atmospheric loss minus miscellaneous losses. By substituting all these parameters, here we are getting the power of the receiving antenna, that is minus 113.5. Now the noise power. To calculate the noise power, here we have N is equal to K plus TS. TS is the system noise temperature plus BN. K already we have. And TS. TS is the system noise temperature, that is T antenna plus TLNA. In our previous videos also we had seen about this system noise temperature, T antenna plus TLNA. So here in clear sky case, that means clear sky without any rain attenuation. Here we are not considering any rain attenuation. Without any rain attenuation in clear sky case, the low noise temperature, that is the system noise temperature, is 45 K. In the sky noise temperature due to 0.2 dB attenuation is 13 K. Therefore, the system noise temperature is 45 K plus 13. So, the system noise temperature here we are getting is 58 K, and converting this into decibels, we are getting 17.6 dB. And coming to the noise bandwidth, here the bandwidth already given. The bandwidth is given. So the given bandwidth is 30 megahertz. So converting this bandwidth 30 megahertz into decibels, dBH. So here for 30 megahertz of bandwidth, by after converting into decibels, we are getting this 74.8 dB hertz. And now calculating for the noise power, that is noise power N is equal to K plus TS plus BN. So K and substituting TS and substituting BN, we are getting the noise power is minus 136.2 dB watts. Therefore, the carrier to noise ratio is given by CNR is equal to PR minus N. That is signal power minus noise power. Signal power minus noise power. So therefore CNR is equal to signal power already we had obtained and noise power is obtained. Therefore CNR is equal to 22.7 dB. So that, but the required CNR is only 14 dB. Only 14 dB. And the obtained CNR is 22.7 dB. So that here we can say the C band is effectively working to receive the signals. In a clear sky case, the C band, by using C band, the signals are effectively received by the receiving antenna.